Hello, everyone. So, welcome back to the good stuff that we have been doing. And today we're going to compute this beautiful integral we have at our hand here. It says this is the integral from negative infinity to plus infinity of tan inverse of square root of x squared plus 2 divided by 1 plus s squared times square root of s squared plus 2. Now, to do this, we're going to use a very non-standard technique, and we're going to use a formula for tan inverse of x. Let's say that tan inverse of x is equals to the integral from 0 to 1 of x divided by 1 plus x squared y squared dy. So it says if you compute this integral, you should get tan inverse of x. And let's see whether this is true. We can take u to be xy. Now, if that is the case, then du would be x dy. So basically, x dy will be du, and this will be integral from 0. Of course, when y is 0, u would be 0, and when y is 1, u will be x. So this will be integral from 0 to x of du divided by 1 plus u squared. Now, basically, this will be equal to tan inverse of u from 0 to x. Now, tan inverse of 0 being 0, you will have this as equals to tan inverse of x. So basically, tan inverse of x equals this integral. That is what we have shown here. And we can take advantage of this fact by recalling that we're going to recall, okay, this is recall that tan inverse of square root of x squared plus 2 should equal the integral from 0 to 1. So now x is playing the role of square root x squared plus 2, and you should have square root of x squared plus 2, and you're going to divide this by 1 plus, then you have an x squared plus 2 times y squared dy. So this is a formula we're going to use to solve this our problem. So what we do is that this integral here, this is our integral here, which is I being equals to the integral. Of course, we can take this as twice the integral from 0 to infinity, because this is an even function. It doesn't matter whether x is positive or negative, it is still going to be the same expression. So we can take this as twice the integral from 0 to infinity. Then you would have tan inverse. Now, you have tan inverse of square root of x squared plus 2, all divided by 1 plus x squared. Then you have square root of x squared plus 2 dx. So this here, right here, would be twice the integral from 0 to infinity. So then now you eliminate this tan inverse and just write a 1 over 1 plus x squared times square root of x squared plus 2. Then this tan inverse of x squared plus 2 will replace it by the integral from 0 to 1 of square root of x squared plus 2, all divided by, hold on, all divided by 1 plus x squared plus 2 times y squared. Then you have dy, then you have dx over here. But let me write it. So dx, yeah. So here it should be dx. Here it should contain dx. So now we could write this as, obviously, this equals, oops, hold on. So obviously, yeah, this equals, now this, they can cancel out, and you end up with twice the integral from 0 to infinity times the integral from 0 to 1 of 1 divided by, so you have a division, one plus x squared times what? 1 plus 2y squared x squared. Then you would have dy dx. Now, what have we done here? We have successfully started off with this, our integral here, and then we ended up with this integral. Now, this may look like a backward step, because if you look at it here, we are essentially ending up with a complicated expression. But as complicated as this may be, I even prefer this over this. And the reason is very simple. Tan inverse of x is not easy to find out what are you even going to do with tan inverse of x. It's not easy to simplify. And even if you may try to say, okay, let's do partial fraction, you can't do partial fraction here. But on the other hand here, the good thing about this is that we don't really have a tan inverse of x here. So that is one thing. Another thing here is that we don't even have a square root term. So we can even do partial fraction, which is what we're going to do next. So you can see that this is much more flexible, even though it may look a bit more complicated, but it's very, very much better to work with this than to work with the formal expression. So now, if we do partial fraction on this, like if you put this in partial fraction, which you can, of course, do yourself, you will end up with twice the integral from 0 to infinity of times the integral from 0 to 1. Then you would end up with 1 over 1 plus y squared times 1 over 1 plus x squared minus y squared all divided by um all divided by 1 plus 2y squared plus x squared. So I already did this myself, so you can do it to find out that they are equal, the y dx. Now what we're going to do is that we're going to switch the order of integration. So instead of starting from dx, we're going to start from instead of starting from dy, we're going to start from dx and then do dy later on. So basically, this will equal twice the integral from 0 to 1. Of course, when you switch the order, you have to switch this. You have to bring 0 to 1 outside and 0 to infinity inside. So this will give you 1 over 1 plus y squared. So then you end up with something like the integral from 0 to infinity of 1 over 1 plus x squared, then dx minus the integral minus y squared times the integral from 0 to infinity of 1 over 1 plus 2y squared plus x squared dx. Then you would have dy. So if we are going to first of all do dx before doing dy. So let's move on. Then this would end up being, this is twice the integral from 0 to 1 of 1 over 1 plus y squared times. Now, of course, this is basically pi over 2. Okay, we can just say this is equal to tan inverse of x. And then we're taking the limit to 0 to infinity, but the result will be pi over 2 regardless. So now we can divide. Okay, there's a y squared here, of course. That's a mistake. There's a y squared here. Yeah. So now we can divide both sides by this y squared, and we get the integral from 0 to infinity of 1 over, then you have 1 plus 2y squared divided by y squared plus x squared. So that would be dx, and then everything would be dy. Now, the next line of solution here is going to be twice the integral from 0 to 1 of 1 over 1 plus y squared. Then you have pi over 2 right there. Then minus here you have, if you do it, you're going to get y divided by square root of 1 plus 2y squared times tan inverse of xy all divided by square root of 1 plus 2y squared. And then you would, this would be equals to dy. This everything will be dy. So then you would end up with this, you end up with twice the integral from 0 to 1 of 1 over 1 plus y squared. Then you have pi over 4. So pi over 2 minus here, when the limit of integration is from 0 to infinity. So when we get infinity, we get pi over 2. So you get a y, so you get a pi over 2 times what? Y divided by square root of 1 plus 2y squared. So everything becomes dy. So when all is said and done, you will get a pi times the integral from 0 to 1 of dy all divided by 1 plus y squared minus, so you will still get pi times the integral from 0 to 1 of, you get y divided by square root of 1 plus y squared square root of 1 plus 2y squared. Now, so dy here. So now this last integral, I will do it in a different video, and I will put the link in the description. So if you want to see how I compute this integral, please check the description, and we're going to you're going to enjoy it. It's very interesting in the integral, but it's not too hard to compute. So basically, you will get a pi multiplied by, this is pi over 4, because you get tan inverse of 1. So, and then this is minus pi times pi over 12. So essentially, you will get pi squared over 4, or minus pi squared over 12, which is going to be pi squared over 6. And that is what we have with us, that this integral right here is equals to pi squared over 6. So thank you for watching this video, and please do check out the next video. I'm going to show how I compute this beautiful integral. Thank you very much, and please do have a nice day. Bye.